Welcome to episode 8 of the Quantum Space Innovating Trust podcast, The Quantum Time Shift. In this special episode, we dive into one of the most intriguing frontiers in modern physics, quantum time. Over the past year, theory and experiment have converged to show that time is not always linear, not always one-dimensional, and perhaps not even fundamental. We'll take you from the bold theories that challenge our deepest assumptions, to the laboratory breakthroughs that are bending the clock, and finally to what this means for quantum computing, secure communications, and the infrastructures we rely on every day. If qubits are the processors of the future, then quantum time is the operating system, and mastering it could define the quantum age. This is episode 8, The Quantum Time Shift.
Time. It's everywhere, isn't it? But it's also maybe the most mysterious thing about our reality.
Absolutely. We've treated it so simply for so long.
Right, like this universal metronome, Newton's idea of absolute time, ticking the same for everyone.
That gave us classical physics, which works great, mostly.
Until Einstein came along and showed us it's actually relative, malleable, part of space-time itself. It slows down near heavy stuff or when you go really fast.
A huge shift.
Yeah.
But then you hit quantum mechanics.
Exactly, and suddenly time becomes, awkward, an outsider.
Yeah, it's not something you measure easily like position or spin.
Yeah.
It behaves more like a parameter in the equations, kind of external. It organizes things, but doesn't feel like it belongs.
So today we're doing a deep dive into this whole concept of quantum time. What's the mission? First, we'll explore the really radical theory that maybe time isn't fundamental at all. Then we'll look at the experimental breakthroughs around 2025, the stuff that proved, manipulation is possible in the lab.
Real-world evidence. Crucial.
And finally, how this strange new view of time is already shaping the infrastructure of the quantum age. It's becoming indispensable.
It really is. And this awkwardness, it stems from something physicists call the problem of time. You mentioned observables, things with quantum operators like position, momentum, spin.
Right.
But for time, we've lacked a good operator for decades. Pauli's theorem touches on the implications of this too. It means time felt locked outside the quantum system.
So the whole scientific community basically had to ask, okay, if it doesn't act fundamental, maybe it just isn't.
Precisely.
What if we just scrapped the whole idea of time as this universal river?
That's the core question now. Is time fundamental or is it emergent? Think about temperature.
Okay.
A single water molecule doesn't have a temperature, right? It just has kinetic energy. But get billions of them together, look at their collective jiggling, and boom, temperature emerges.
Ah, I see. So time might be like that.
That's the idea. It could emerge from, relationships, correlations between quantum things, rather than being some underlying cosmic clock.
Okay, let's unpack that. If time emerges from relationships, how does that work in a quantum model? What does it look like?
Well, one of the big ideas here is the Pagewater's mechanism. It suggests time literally emerges from entanglement.
Entanglement itself.
Yeah. Instead of one big universe with the time flowing through it, you conceptually split the universe into two parts. Think of one part as a clock.
Okay.
And the other part as the rest of the system. And these two parts are entangled.
So the clock is tangled up with the thing it's supposed to be measuring? That sounds weird.
It is weird, but it works mathematically. When you look at the rest of the system based on the state of the entangled clock, like, okay, the clock says tick 7, then you see evolution, change, what we call time.
So time isn't a river then, it's more like a web, a network of these correlations.
Exactly, a network of relationships. Your personal feeling of time passing comes from, in this view, your own internal clocks being entangled with everything else.
Wow, okay. So if time is just a correlation, what about the arrow of time? Entropy, things breaking down, eggs not unscrambling. That feels pretty fundamental.
It feels fundamental, absolutely.
Yeah.
But in this quantum view, that one-way arrow is also seen as emergent, not baked into the deepest laws.
But things do decay. Order does go to disorder.
Macroscopically, yes. Entropy wins on our scale. But the basic equations of quantum mechanics, they actually work forwards or backwards in time. They're reversible. So the arrow we see is more like a statistical effect, a property that emerges from large systems And microscopically, people are actually starting to play with this reversibility.
Play with it how?
There's this thing called a quantum switch. Researchers have used it to manipulate photons, essentially, while nudging them back towards earlier quantum states.
Like hitting a tiny quantum undo button.
Sort of.
Yeah.
On a very small scale, yes. It's like a controlled rewind.
That's already amazing. But then I read about things that sound even stranger, like negative time or nonlinear time, where quantum effects mess with the sequence of events.
Yes. That's where quantum intuition really clashes with our everyday experience. There have been experiments with photons going through certain materials where the peak of the light pulse seems to leave the material before it actually entered. Just fractionally, but still.
Wait, how is that possible? Does that mean time travel?
No, not paradox time travel. It doesn't violate causality in the grand sense. But it shows how our classical idea of A must happen before B can get fuzzy at the quantum level. Quantum interference can scramble the perceived order. Events can be superposed, not just sequential.
Okay. Superposed order. My head hurts a little. And this is where it gets really interesting, I think. If the flow we see is just a construct, what if time isn't just one dimension?
That is a truly radical theoretical step, yes.
Sure.
Some frameworks propose that time might actually have 3 dimensions, just like space has height, width, depth.
3 dimensions of time. So are we just stuck moving along one track, experiencing only one of these time dimensions?
That's the speculation. What feels like our single forward-moving time could just be a projection, a shadow of a much richer, multidimensional temporal structure.
So 2 people could literally experience the order of events differently, not just due to relativity, but due to this deeper structure.
Potentially. It opens up entirely new ways to think about the mathematics of the universe. It's mind-bending stuff.
It really is. Which brings us neatly from the theory to the lab, because the sources say 2025 was a key year when quantum time stopped being just math and became, well, engineering.
Exactly. That's the pivot. One of the first big experimental proofs came out of Stockholm. They were focused on synchronization.
Syncing clocks.
But using entangled photons. They sent them across a citywide fiber network and managed to sync distant clocks with picosecond accuracy. It's incredibly precise.
Picoseconds. Okay, that's fast. But why should, you care? What's the big deal about syncing clocks with entanglement?
Trust. Security. That's the big deal. This timing signal is fundamentally tamper-proof. Unlike GPS, right, which uses classical radio signals, those can be jammed, they can be fake spoofed.
Right. I've heard about GPS spoofing.
With entanglement, you can verify the signal using quantum measurements, like quantum tomography. If anyone messes with the photons, the entanglement breaks, the correlation vanishes. You know instantly something's wrong.
Okay. So it's a secure time signal you can actually trust, built on quantum physics itself.
Precisely. A verifiable timing backbone.
And this isn't just happening in one city. There was that big international project linking optical clocks across, 6 countries?
Yes, linking 10 of the world's best clocks, the optical lattice clocks. We're talking national labs like PTB in Germany, NPL in the UK, ZERD in France.
The places that literally define the second.
Exactly. And this network is so stable, it's pushing the world towards redefining the SI second itself, moving beyond the old cesium standard to these optical systems.
So these aren't just lab toys. They're becoming the bedrock for global infrastructure, like communications, data centers.
Absolutely essential. The timing requirements are getting stricter and stricter.
But maybe the wildest experimental result from around that time, the certification of indefinite causal order, ICO.
ICO, yes. That was huge.
We touched on it, the idea that operations can happen without a fixed sequence. A before B and B before A, somehow at the same time.
In superposition, yes. Not one then the other, but both orders existing as possibilities simultaneously until measured.
But wait, if causality isn't fixed, how do you build anything? Computers rely on steps happening in order, don't they? A, then B, then C.
That's our classical thinking. But quantum mechanics flips it. This lack of fixed order turns out to be a resource, not a bug.
A resource? How?
Well, this ICO was certified, and not just theoretically. It was certified device independently, meaning you don't have to trust the specific machine with something like 24 sigma confidence.
Which is incredibly certain, right?
Astronomically certain. Certifying ICO like this means it's now a real physical quantum resource you can use. Just like entanglement became a resource after the Bell test proved it was real, we can actually program with non-causal order now.
Programming with non-causal order, okay. Yeah. And these new tools, these quantum clocks and resources, are also letting physicists probe that other giant theory, general relativity.
Yes, trying to bridge the gap between quantum mechanics and gravity. The proposal is to use these entangled
The
clocks.
super precise ones.
Right. Place them in different gravity fields, like one lower down, one higher up, or moving at different speeds.
Because relativity says time runs differently in those situations.
Exactly. Time dilation. Gravity makes time run slower. But the effects are tiny at scales we can usually manage. Classical clocks just aren't sensitive enough for some of the subtle quantum gravity effects we expect.
But entangled clocks are.
The proposal suggests they are. Because they rely on correlations, they can pick up these incredibly subtle differences in how time flows. It's a realistic way to finally test quantum theory in curved space-time using tech we actually have or are building.
Okay, so let's bring this back home. We've got emergent time, reversible time, maybe multidimensional time, lab-verified synchronization, indefinite causality. What does this actually mean for the systems you and I rely on every day?
It means quantum time is becoming, you could say, the hidden operating system of the quantum age.
The operating system? How so? Especially for quantum computing.
For quantum computing, trusted timing isn't just nice to have, it's existential.
Existential, why?
Qubits evolve incredibly fast. And quantum error correction, which is vital, depends utterly on knowing exactly when things happen. If your timing is off by even a tiny fraction for a measurement,
Yeah.
the error syndrome you measure is wrong. You think you know where the error is, but you don't. A tiny physical error you could have corrected becomes a devastating logical error that kills the whole computation.
Ah, so you need that perfect verified timing.
Which is where those entanglement-verified clocks come in again. They provide that trusted heartbeat for distributed quantum systems. You can have quantum computers miles apart working together as if they were one machine, perfectly synchronized.
And what about that time reversibility, the undo button idea? Is that just theoretical or?
It opens up really speculative but potentially revolutionary paths for error correction.
Mm-hmm.
The current way is massive redundancy, using tons of physical qubits just to protect one logical qubit.
Right, the overhead is huge.
But imagine if you could use that quantum switch idea.
Yeah.
If you could detect decoherence starting and just rewind that specific qubit back a tiny fraction of a second to before the error fully happened.
You could erase the error directly using time flow itself.
Potentially. It would be an incredibly powerful tool, maybe simplifying quantum computer design enormously down the line. It's still speculative, but the physics allows for it in principle.
An indefinite causal order that's not just weird physics. You said it's a resource for algorithms.
Absolutely. ICO can actually reduce the complexity for certain types of problems. By running different computational steps in a superposition of orders, you can sometimes get the answer faster, or using fewer resources.
So future quantum algorithms might actually have steps that are like do A and B in indefinite order.
Exactly. It expands the whole toolbox for quantum programmers beyond just standard gates.
Okay, but scaling this up globally, doesn't relativity throw a wrench in the works? If time runs differently on a satellite than on Earth, how do you keep a global quantum network synchronized?
It absolutely does. Relativity becomes a real headache at this level of precision. Gravitational time differences, speed differences, they all mess with synchronization.
So how do you fix it?
Well, the beauty is the same entangled clock systems that give you security can also measure and correct for relativity.
Ah, because they are sensitive to those time differences anyway.
Precisely. By watching how the correlations drift between clocks in different places, say Earth and orbit, you can figure out the relativistic effects and adjust for them in real time. It makes a truly global, relativity-proof quantum internet feasible.
Amazing. So beyond the pure science and computing, what about, say, banks or navigation?
Huge implications. For finance, think about high-frequency trading. Quantum-verified time gives you a completely tamper-proof way to sequence transactions. Could it level the playing field? Reduce fraud based on tiny timing advantages? Possibly.
A verifiable order of events?
And for navigation. Current GPS is vulnerable. Jamming, spoofing, it happens. Quantum timing provides an underlying backbone that's immune to that kind of classical manipulation. An unshakable reference for position.
So, wrapping this up, the journey here has been immense. We've gone from time as this philosophical puzzle.
The problem of time, yeah. Pauli's theorem implication.
Right, that deep theoretical unease. To time as an engineered resource, something we can measure, verify, manipulate, and build into technology.
That's the transformation. Quantum time is moving from the physics department into engineering labs and, increasingly, into real-world infrastructure. It's changing how we build communication networks, financial systems, maybe even computers themselves.
It really feels like a fundamental shift in how we relate to, well, reality.
And maybe that's the final thought to leave people with. The implications aren't just technological, they're philosophical, maybe even cultural.
How so?
Well, if physics is telling us that time, this thing that structures our entire lives, our memories, our sense of history, isn't fundamental, that it emerges, that its flow can be at least locally manipulated or even non-sequential.
Yeah.
What does that really mean for us, for how we understand sequence, cause and effect, memory itself? What does it mean to live in the universe where the river of time might just be an illusion, arising from a deeper, stranger, quantum reality?
That is definitely something to think about. A universe where time itself is a construct. Wow.
You've been listening to Episode 8 of the Quantum Space Innovating Trust podcast, The Quantum Time Shift. We've explored how theory is reshaping our understanding of time, how experiments are bending the clock in the lab, and how these breakthroughs are building the hidden infrastructure for quantum computing and communications. As always, you can find more analysis and the full article series on our website at thequantumspace.org. Thanks for joining us on this journey into the strange and fascinating world of quantum time. This was Innovating Trust, a quantum space podcast edited and produced by Crown Communications.